Welcome, everybody. We'll start in a couple of minutes when people had a chance to enter. Just wait one other minute before we get started. All right. Welcome, everybody, to the SoDa Symposium. This is a symposium that we have been running through the Social Data Science Center for quite a while. We have made in the past webinars available via a recording, and this one too will be recorded and made available on the SoDa website sometime next week. We will also have a lot of time for questions at the end of the presentation. Our presenters here are planning for 40 minutes presentation and then a Q&A with anything that you want to ask. To facilitate that, we recommend that you use on the bottom of the screen, you should see the possibilities to enter your question in the Q&A portion. And so I recommend doing that, and then we can see your questions and field it to the participant. But feel free to also indicate that you would like to talk in person, and then Jody will unmute you. All right. So this said, I am delighted to have our last recipient of the SoDa Seed Grant series here. Tracy Sweet is an associate professor in the Department of Human Development and Quantitative Methods. She completed her PhD in statistics at Carnegie Mellon University and an AM in mathematics at Morgan State University. Her research focuses on methods for social network analysis and machine learning. She serves as Associate Director for Research for UMCP for the Marian Longitudinal Data System Center, dear to my heart, and is currently overseeing projects applying data science and statistical methods to large education data. If we don't talk about the presentation, we certainly have a lot to talk about that part. Dr. Sweet is committed to improving equity in the fields of statistics and quantitative methods. And with her is her doctoral student, Ashani Jayasekera. I practiced this, but not enough. Who, as a PhD candidate in quantitative methods, will be graduating next year, and the work she's presenting today is part of her dissertation. She earned her master in measurement and statistics and evaluation, also here at UMD, and her BS in mathematics, also at UMD, but Baltimore County. Her research interests include machine learning, natural language processing, the analysis of complex data structures, as well as the intersection of data science and QuantCrit. I'm looking forward to learn what that is. Recent research projects include work on the efficacy of supervised machine learning and causal inference, the utilization of propensity scores to provide measures of school quality, and the impacts of missing data on social network models. With this, I welcome you, Ashani, and turn over the mic to you. Thank you very much.
Thank you. Let me share my screen. everything look okay on your end?
It does. Thank you.
Great. Okay, hi everyone. Thank you for being here today. So I'm going to talk to you about some of the work I'm doing on utilizing data preprocessing strategies and resampling to improve the fairness of machine learning predictions, specifically supervised machine learning predictions when there are different subpopulations of individuals in data. This work was and is still being done in collaboration with my advisors, Dr. Tracy Sweet, who's on the panel today, and Dr. Laura Stapleton. So let's begin with some background on machine learning and why fairness and equity matters in this context. So machine learning, like we know, is a type of AI that involves constructing algorithms that learn from existing data to make predictions on new unseen data. And this is supervised machine learning as opposed to unsupervised, where you do clustering or finding patterns when you don't have labels. In terms of a general application, algorithms have been used to recommend streaming, recommend content on streaming services and social media. In the medical field, algorithms have been used to precisely diagnose diseases. And in education, machine learning has been used to predict student retention and thereby help institutions intervene before students drop out and conduct automated essay scoring via natural language processing and large language models, which are part of the broader ML canon. However, like humans, these algorithms can be vulnerable to certain biases that can make predictions and thereby decisions that are unfair to certain populations. So for example, if you were to Google recommend jobs that are in my field in the Google recommendation AI, men are often systematically recommended higher salaried positions than women, even if they have the same qualifications. So fairness, when we define this term, we can see that there are many different definitions one can associate. So if we start with our social definition, fairness is the absence of any prejudice towards a specific individual or group based on their characteristics. In the algorithmic fairness literature, bias or unfairness refers to when an algorithm's predictive performance, unjustifiably varies across population subgroups. So that makes the unfair model one that makes predictions that are skewed towards one group or one individual over others. So if you were to look, for example, at a loan approval algorithm, it may consistently deny loans to qualified applicants from one particular ethnic group at higher rates than equally qualified applicants from another group. So that would be an example of algorithmic unfairness because one group is being systematically denied over another. So far I've used two different terms. I've used the terms bias and unfairness in my talk, and that's because there's a lot of inconsistency in the language that exists in literature. So the terms bias, discrimination, unfairness are often used interchangeably, which can create a lot of confusion. However, because the term bias is a very specific meaning in inferential statistics, so bias in inferential statistics is the deviation of an estimate from the population truth, researchers in this specific field like to use the terms fair and unfair to differentiate between the concepts. I have a tendency to go back and forth, so I want you guys to know that bias and unfairness, when I'm referring to these two things or concepts, mean the same thing. Marabi in 2021 defined fairness in machine learning as the absence of favoritism in the algorithm's results based solely on an observation's inherent characteristics. And so fairness assessments often focus on differences in algorithmic performance across sensitive or protected attributes, like race and gender, that have been historically used to marginalize certain individuals in society. And there are two main facets of fairness. There's group fairness and individual fairness. And so when a researcher is trying to determine whether their algorithm is fair, it is imperative that they first select the appropriate definition of fairness that is important to them, because I'll determine which of the many potential fairness conditions that they need to meet in order for an algorithm to be deemed fair. So like I said, there are two different classes of fairness measures. The first class are measures that address individual fairness, which is the idea that algorithms should produce similar predictions for similar individuals, no matter their sensitive attribute group. But there's several different ways to operationalize individual fairness. The three that are listed here I'm going to talk about in my next slide. They are fairness through unawareness, fairness through awareness, and counterfactual fairness. So fairness through unawareness suggests that a machine learning algorithm should be able to achieve fair outcomes by eliminating sensitive attributes and their correlated features as predictors. So this idea is fairly simple. So if the algorithm cannot see race or gender, for example, it cannot discriminate based on those factors. However, this approach has several limitations because if you're eliminating all the sensitive predictor as well as any of the correlated or proxy values, you're going to really be limiting the information available to the algorithm to make a prediction. Fairness through awareness takes a different approach. So it says an algorithm should produce similar predictions for individuals who are deemed to be similar on some predefined distance metric. So that requires us to define what similar means. And then counterfactual fairness asks, would an observation's prediction remain the same if that individual belonged to a different demographic group? So if you change someone's race or gender in the data set, you cannot change that in actuality. Would that change their prediction if everything else were to stay the same? And if it does change, then that algorithm could be deemed to be unfair. So the other class of fairness is the measure of group fairness, which is the idea that algorithms need to treat different groups similarly to ensure equitable outcomes. So there should be similar levels of accuracy, precision, and other measures of algorithmic performance across different sensitive groups. And like I did with individual fairness, there are several examples of measures of group fairness listed. So the first measure that I want to talk about is statistical parity, but before I get there, we want to talk about some notation. So we're going to denote the discriminated group as x sub s equals 1 and the privileged group as x sub s equals 0. So what you could think about that is like people of color could be the discriminated group, s sub x equals 1, and the privileged group could be white individuals, which is x sub s equals 0. So statistical parity, which is also called demographic parity, requires that the probability of a positive outcome, and so in our loan approval example, that could be that they get the loan, should be the same across different demographic or sensitive attribute groups. So mathematically, that means that the probability of a successful prediction, given that they belong to the discriminated group, should equal the probability of success, given that they belong to the privileged group. Disparate impact is related but measures this as a ratio. So it's the expected probability of success should be the same among different sensitive groups. So if the algorithm is perfectly fair, then the disparate impact measure should equal 1. And if it's not fair at all, it should equal 0. And this metric will take the minimum of 2 ratios to ensure that we're capturing disadvantage in either direction. The next one is equalized odds, which requires that all groups, so all of our sensitive groups, have equal true positive rates and equal false positive rates. So that means that the prediction of success is independent of the sensitive attribute when the actual outcome is held fixed, when the true value of y is either 0 or 1. Equal opportunity is a relaxation of equalized odds, which only requires that all groups have a equal true positive rate when the prediction is independent of the sensitive attribute, when the actual outcome is 1. So only when y equals 1. So we have individual fairness and group fairness. And so the idea, next question someone might ask was like, which one do you use? And so the decision to satisfy either individual or group fairness depends on your purpose. What do you care most about? Do you care that the individual predictions are fair, or do you rather care more about the equity across groups? So in our studies, we're going to focus on group fairness because we're interested in ensuring equitable outcomes across demographic or sensitive groups, which is often the concern in policy and in organizational context. However, individual fairness is equally important in contexts where personalized treatment is paramount. So I'm going to talk first about a pilot study that I did last year before going into like the work that I'm currently working on. So the purpose of this pilot study was, since that we've established that there are fairness concerns when machine learning applications are used, and there's several metrics that could measure whether an algorithm is fair or unfair, what can we do to mitigate those concerns? So we can address these concerns at 3 different stages of the supervised machine learning pipeline. You can do something called preprocessing techniques, which modify the data before training. You can do something called in-processing techniques, which modify the algorithm during the training process. and then post-processing techniques which modify the predictions after training. And our pilot study focused specifically on pre-processing techniques, which I'll explain in more detail in a few slides. So this is the typical machine learning supervised process. So you have a data set, typically very large, which are going to then which have labels or outcomes assigned to each observation. Then you're going to take that data set and divide it into a test set and a training set. Using that training set, you're going to train an algorithm, which will result in a final model, which is then applied to a test set, which then can be used to make predictions. Based on these predictions, you're going to evaluate the performance of this final trained model, comparing the predicted values to the true outcome labels in our test set. Pre-processing refers to steps that are taken between the selection of our training data and the actual training of our algorithm. These methods, these pre-processing methods, modify the training data in an effort to reduce any sort of imbalance or inconsistency that exists in the training data to help improve fairness when the models are trained and then tested on the test set. So these interventions happen right here, in between the selection of our training set and the actual algorithm training process. So the goal is to create a more balanced training data set, which will lead to fairer predictions once your algorithm is trained. And so examples of some of these pre-processing methods could be to modify the values of the training data points themselves. So remember we talked about fairness through unawareness, where we simply remove sensitive attributes. You could do that. You could also remove certain data points or observations from our training set entirely, which is what fair situation does. So fair situation removes problematic observations, where if you were to switch the membership of the sensitive attribute for each observation and then train the models and get predictions, if those predicted values change simply because of the value of the sensitive attribute, that observation is determined to be problematic and you can remove that. You can also manipulate the training data set distribution via undersampling or oversampling. So for example, if you only have 10% of our data set has positive outcomes, we can essentially bootstrap or create more examples of positive outcomes to balance our data set. And so there's more information when the model is training on that minority outcome. So then you can have better results for that outcome. In-processing methods incorporate fairness constraints or objectives into the training process itself. So they adjust the way the machine learning model is trained in an effort to improve fairness, and that happens while the algorithm is actually training. So a couple of examples of how you can apply in-processing techniques. So you can add in a fairness constraint into the loss function. So when an algorithm is trained, it's trying to optimize some sort of loss function. So if you add the fairness constraint into the loss function, you're trying to optimize not only model performance, but also optimize model fairness. You can also do something called adversarial debiasing, which trains a model to simultaneously optimize model accuracy while reducing the ability to determine the value of the sensitive predictor. You can also do something completely different from that, where you, instead of fitting one algorithm or training one algorithm across the entire training set, you're going to fit separate models across each of our sensitive groups, which is actually something we explore in our studies. And then our last set of techniques we can apply are done post-processing. So this is after the algorithm is trained. And these are done after we train the model, but before we make our final predictions. So for example, if you have some sort of classification task, typically we might use 0.5 as our threshold for 0.5 of our threshold to make our decisions. But maybe that's not the best for all of our data or all our different groups. So you might want to create a different optimal thresholds across different sensitive groups in order to achieve our statistical parity or other measures of group fairness. So where does our study lie? So we're mainly focusing on that pre-processing approach between our initial selection of our training set and before our algorithm training. We want to modify the training data before any sort of algorithm training. A small section of our study also explores in-processing, where we're going to fit separate models across the different sensitive groups and see whether we need to do any sort of pre-processing at all if we do that. So specifically, our study examines two key decisions. First, should we apply data preprocessing based on the outcome class, the sensitive group, or both in order to have fairness as well as maintain good model performance? Or should we train our algorithms separately across sensitive groups or together on the full data set? We're exploring essentially the interaction between the preprocessing decisions and how we apply our classification algorithms. And so this area represents the space that we're investigating. So for our pilot study, I want to give you guys a motivating scenario that grounds this work. So suppose we have different universities that task us to examine their mission processes and decisions. So this is a binary outcome. The student either gets into the school or they do not. And these universities are interested in developing an admissions process that's fair across different sensitive demographic groups. And they want to use machine learning to help make these admissions decisions, but they want to ensure that these algorithms are fair at the group level. That is, different demographic groups are going to be treated equitably. And this is exactly the real world type of real world problem our research is trying to address. So the research questions for this pilot were: under what conditions, if any, do the data preprocessing techniques outperform not doing any sort of preprocessing at all and developing models that result in fair predictions? And then could we use the separate application of these machine learning algorithms across different subgroups to improve algorithmic fairness while maintaining overall classification accuracy? So we did a simulation study, so we had to generate our data. So the data for this pilot simulation were generated using a logistic regression model, where our outcome is a binary outcome. They either get into the school or they do not. And success is when y equals 1. The sensitive attribute is a binary variable as well, right here, where you either have membership of the discriminated class or membership of the privileged class. There were a total of 8 different main effects predictors that were generated to reflect real-life conditions of Maryland public schools, respect to gender distribution, the English language learner status, parental education attainment, SAT scores, and others. And then there's this term right here. These are moderator terms. So 6 of these main effects predictors are crossed with our sensitive attribute to create moderator effects. So this was to make it so that there are differential effects of these predictors when someone is a member of this discriminated class. So this means that these predictors work differently if an individual is a member of the discriminated class versus the privileged group, which reflects like this real world complexity in data. However, these moderators are not considered when we applied our machine learning algorithms to the generated data, because without a priori knowledge, a researcher would not know to include these terms when they're fitting the models onto the data. So there are several manipulated conditions in terms of data generation. We had different the level of outcome class imbalance is manipulated to either be extremely imbalanced or more balanced. So maybe you have a school that has a very high level of rejection and a very low level of acceptance, and one that's more balanced between the two conditions. There are 3 different data preprocessing methods we looked at. That includes doing nothing and then using 2 different oversampling methods, either randomly oversampling or using something called SMOTE-NC. We oversampled either on the outcome variable, the sensitive attribute variable, or both of them. And then there are 4 different machine learning algorithms that were applied to the training data, either applied separately across the sensitive attribute or across the entire training data set at once. Because this was a pilot, the sample size is quite small. It's only around 1,000 observations because this was a proof of concept. There were, again, 8 different main effects predictors and 6 moderators. The sensitive attribute was set to be around 22% of the observations are members of the discriminated group. And that's to match like the Hispanic population in the Maryland public schools. And we did 500 replications. So speaking more about like the data preprocessing and oversampling methods that are used. So the first is that we do nothing. We don't do any sort of preprocessing. This is kind of baseline. And then we did 2 different oversampling methods. Oversampling is an approach that's traditionally employed when you have outcome class imbalance. And so we're trying to extend that to also address fairness concerns. So random oversampling will bootstrap minority observations until balance with the majority observations is achieved. And SMOTE is a more sophisticated version of oversampling, SMOTE-NC is an extension of SMOTE, and SMOTE essentially generates synthetic minority observations by interpolating continuous features and using the mode of our nearest neighbors for categorical features. And so we're essentially creating fake data that have that minority observation. So SMOTE in more detail looks something like this. So in the leftmost panel, panel A, we have minority observations that are in green and majority observations that are in blue. You're going to select one minority observation, this point in black, and in this case, select 3 nearest neighbors that are also minority observations. Then you're going to select one of these 3 at random, which is this brown point. And then you're going to select a random point in the distance between your parent point and your selected nearest neighbor to create your synthetic minority observation. SMOTE, the original SMOTE algorithm, is intended to handle only continuous values. SMOTE-NC is an extension of SMOTE that accommodates nominal as well as continuous values, which is why I needed to use that for this pilot study, because we do have some nominal and categorical variables in our data generation. And oversampling, like I said, is again traditionally used only to address outcome class imbalance, but we can also address imbalance in any variable in the data, including a predictor like our sensitive attribute. So oversampling was done with respect to the outcome, so whether someone was accepted into university, for example, the sensitive attribute, the ethnicity variable, or both. And both is more complex than the other 2 oversampling techniques. So the training data set is first divided based on the value of our sensitive attribute. And then within each of these new data sets, the number of instances will be equalized to the number to respect to the outcome y by oversampling. So the conditions were then evaluated on 2 different metrics, fairness metrics. The first was disparate impact, the second one is misclassification rate. So disparate impact, which you talked about earlier, is a measure of whether the expected predicted probability of success is independent of our sensitive attribute. There are no set statistical guidelines for this measure, but the Equal Opportunity Commission says that if our disparate impact value falls between 0.8 and 1.25, then that model can be deemed fair. This is that 80% rule of thumb. So we're using this measure, we're going to look at the proportion of our replications that meet this criteria. And the misclassification rate is a measure of the proportion of observations that are incorrectly predicted by the algorithm. So over the replications, we can get an average misclassification rate for the algorithm overall and for each of our sensitive groups. And using comparative analysis, we can compare the misclassification rates for our privileged and discriminated groups. Misclassification can also be calculated as 1 minus our accuracy using the traditional confusion matrix. So let's look at some results. So let's first look at the proportion of disparate impact metrics that cannot be calculated. So disparate impact is a ratio, so it's possible to get a value of 0 over 0. And so 0 over 0 would mean that the rate of predicted successes is equivalent for both groups. So if you go back to our formula, if you have 0 over 0, that means these 2 groups are equivalent to each other. However, that does not indicate that the algorithm is automatically fair. We need to consider context, and class imbalance must also be considered. So on the left, we have the results when we have an outcome class imbalance of 60-40. And on the right is when our outcome class imbalance was set to 90-10 or more extreme condition. So when we have a very large outcome class imbalance, we can see that there's a large proportion of metrics, especially using Lasso, where we have disparate impact metrics that cannot be computed. And that's upwards of 80% when the algorithm is applied to the entire training data set. Even when there is pre-processing with respect to the sensitive attribute, which is in this purple, we can see that anywhere from 18% to 67% are incalculable disparate impact metrics. In comparison, there's relatively little when there is little class imbalance, there are much fewer disparate impact metrics that cannot be calculated. And there's similar results for this one, regardless of the outcome. So, similar results for this outcome. So the separate results are not discussed here. But when we do look at the disparate impact measures that can be calculated, specifically when the outcome imbalance is large, such as in this case, oversampling, which is in this red color, with respect to both variables, outcome and sensitive attribute, which is in the red, results in the largest proportion of instances that meet our 80% rule of thumb. When you oversample only with the outcome, which is in this blue color, you'll see that there are some values that meet our 80% rule of thumb, but most of them are still far away from the threshold. And purple, which is where you oversample only on the sensitive attribute, doesn't find any success at all. So when you look now at comparing the misclassification rates across our groups, the privileged and the discriminated groups, where privileged is in the blue and discriminated is in the red, there's a large discrepancy in the misclassification rate for the two groups when you don't do any sort of pre-processing, which is in this leftmost panel across each of our conditions. Pre-processing with both the outcome and the sensitive attribute, which is in the leftmost of the middle panels, reduces the discrepancy in our misclassification rates between our sensitive groups. But pre-processing with respect to only our outcome, which is in the center of the center panels, exacerbated the difference in the misclassification rates between the two groups. And this is consistent across our different pre-processing methods. However, it's important to note that when you apply pre-processing methods in general, you're going to increase the overall misclassification of the algorithm's predictions, which is to be expected because you're trying to improve the accuracy or the accuracy of the minority class. So you're going to decrease essentially the predictions, the number of accurate predictions overall. So when there is a large imbalance of the outcome data, the improvements in the fairness of the models when oversampling is used comes at a cost of the overall predictive accuracy, like I just said, and this can be upwards of 20–30%. There's a large improvement in the difference in the misclassification rates across sensitive groups when oversampling with respect to both the outcome and the sensitive attribute. And a large proportion of those satisfy the 80% rule of thumb for the disparate impact measure. Oversampling only on the outcome variable exacerbates the discrepancy in the group misclassification rates. So this pilot study had a ton of limitations. We limited the study to a fixed sample size of only 1,000 observations. These methods might perform differently with smaller or larger samples. Machine learning applications typically have very large data sets, so definitely in the future, we're going to increase the number of observations. Our predictors that we generated were not correlated with each other, which is not realistic. Real data have a ton of complex correlation structures, and we only considered a fixed level of the proportion of discriminated individuals in the data. Only a few select algorithms were considered for this study. More complicated methods might result in no pre-processing not need any pre-processing. And then there are also pre-processing techniques that incorporate fairness constraints into these algorithms. So that might be something to explore in the future. So that was what we did last year. And so then this year, we're going to do some work where we're going to expand our pilot study to have more robust and more broader generalizations of these results. So we're going to expand our simulation study to include more realistic data generation mechanisms. So this table shows our planned mechanisms. So we're going to generate data using 6 different data generating models that have and do not have differential predictor effects. So we have a tree-based model that we're adding in, as well as using some boundary-based methods. This will help us understand whether our findings generalize across different types of underlying data structures and whether the relationship between predictors and outcomes could be linear, nonlinear, or more complex interactions, or sharp decision boundaries, and whether we can achieve fairness when we have different data generating models. So when we don't have our differential predictor effects, we don't have that inclusion of the moderating terms. But when we do have moderators included in our model, data generating model. But again, when we fit our algorithms to our data, if there are differential predictor effects when we generate the data, we're not going to include that when we fit the model, because again, an applied researcher would not know to include those if they do not have a priori knowledge of how the data were generated. We're also going to include more predictors in general when we generate the data. So In our pilot study, we only had, I think, 8 main effects predictors. In this one, we're going to have anywhere from 10 to 15. We're also going to expand our examination of imbalance. So we're going to look at various levels of outcome class imbalance, as well as sensitive predictor group imbalance, ranging from our balance condition all the way up to when we have highly imbalanced data. And this comprehensive approach will reveal when preprocessing techniques are most beneficial and when they might not be necessary at all. We're also dramatically expanding the preprocessing methods as well as the classification algorithms we're going to examine. So for preprocessing, we're going to add techniques like fair situation, like I described earlier, where we switch the value of the sensitive attribute. And if that prediction changes, then the observation is removed. We're also going to add something called fair smote. And fair smote works by first dividing our training data into 4 quadrants, which are reflective of the different combinations of sensitive attribute and outcome class. And then you're going to rebalance within those quadrants, so then all 4 quadrants are the same size. In terms of classification algorithms, we're going to look at adding in these more regularized regression models, as well as having more ensemble methods and tree-based methods and support vector machines. Which are more, all of these tend to be more classical classification algorithms, but they are what are commonly used. So hopefully we can see when the combination of preprocessing as well as classification algorithm would result in more fair results. And then we're also going to do a lot more evaluation metrics. So we're going to evaluate not just our fairness, but also our model performance. So for performance, we're going to look at 5 different metrics, including recall, which measures the proportion of actual positive cases that are correctly identified by the model. False alarm, which is the rate at which the model incorrectly labels negative cases as positive. The model accuracy, the model's precision. So precision measures the proportion of predicted positive cases that are actually positive, as well as F1 score, which is the harmonic mean of precision and recall, balancing both of the metrics to give a single performance score. And then for fairness, we're going to look at 5 different metrics, including disparate impact, like we talked about earlier, the average odds difference, which measures the average of the differences in the false positive and true positive rates for the minority and majority sensitive predictor groups, equal opportunity difference, which calculates the difference in the true positive rates between minority and majority sensitive predictor groups to assess fairness in our positive outcomes, statistical parity, and misclassification ratio. And so when we're doing this work, we want to balance having good model performance as well as having good model fairness. So having both of these measures, or having measures for both of these, is really important because you want a good balance between the two. You don't want a really fair model, but then it's fair because it's just a generally really bad model and doesn't make accurate predictions, and vice versa. You don't want a really accurate model that has really good model performance, but then that's because we are not predicting any sort of correct value for our discriminated sensitive group members. What else? We're also going to do an empirical illustration using real data. So we're going to do an empirical analysis using data from the Maryland Longitudinal Data System Center, which links education data across the state. And so our goal will be to predict on-time graduation within 4 to 5 years with a degree, fairly and accurately across different ethnic groups. We have access to a rich set of covariates, including prior academic performance, demographics, and institutional characteristics. And so doing this empirical data analysis will allow us to demonstrate that our simulation findings translate to the real world, and provide concrete guidance to practicing academic researchers. So the goal of the expanded study that I'm doing for my dissertation is to demonstrate that the findings are consistent across a variety of different data generating mechanisms and designs, that they're robust and generalizable. And second, we also want to provide applied researchers with the tools necessary to ensure that their predictions are fair. This is especially critical now in the social sciences, when algorithmic decisions can have profound impacts on people's lives, and especially like when we're doing social science research. Thank you.
Fabulous. Thank you very much. I couldn't hope for a better talk for the SoDa, because this is so clearly machine learning meets survey methodology. And I saw some of our graduates in the audience here, Ting and Stephanie probably will have questions as well. But let me get started while others have a chance to put their questions in the Q&A tab down there. I was wondering if you could revisit for a moment how you did the selection. I would call it stratified sampling, probably what you did. I mean, because you did, I mean, you said you use a sensitive attribute and then you disproportionately take sample from each of the group. I was wondering what
This slide right here.
sampling ratio you used for those, and it looked like in the study extension you will vary that ratio. I would call it weight, but I was just curious to understand your thought process there.
Are you talking about the data pre-processing methods or how I generated the data to begin
The
with?
pre-processing, yeah, when
Yeah.
you decide to select, yeah.
Yeah, so the end goal often is to end up with a balanced grouping, right? So if you have I don't know, like 1,000 observations that have the positive value, you want to end up after you do your pre-processing ending with 1,000 observations of the opposite grouping. And so for random oversampling, you're just going to bootstrap randomly until you end up with that. And SMOTE essentially will select a random value of a minority observation. And then from that, it'll select the nearest neighbors. And so
I see. So this is okay.
Yeah, so it'll select the nearest neighbors. In this case, it's 3. If you have because I have a very small data set in this pilot, but if you have more observations, you can definitely do up to 5, I think is the standard typically. And then from there, you're going to select one of our neighbors at random and then pick a random point in between to create our synthetic observation.
Okay. So it's not necessarily, it can be implicitly a ratio of the size of the minority group. Okay, cool.
Yeah.
We have 2 questions in the Q&A. I'm gonna read out the first one. It's a shame that overall classification accuracy would decrease. Could you do some diagnostic when you see a difference between classification accuracy with and without these methods, and then adjust your algorithm to then include interactions? Or would you still not know the interaction to include?
I have to think about that. Tracy, do you have any
I
ideas?
can answer that one. Yeah, so I think I have kind of 2 responses to this question. The reason that there are these interactions is that's how we're simulating the data. In a real world analysis, we don't actually know how the data came to be, right? So there could be any kind of 2, 3, 4, 7-way interactions that kind of create or cause kind of the data to be what they are. So in that sense, we wouldn't actually know, we may not even have the variables that go into constructing a particular data set. So for Ashani's simulation, she has interactions just to show that we're not always able to fit the algorithm exactly to the data that were generated. It's kind of a way for us to both kind of know what the truth is, but also have some difference between the data generating mechanism and the algorithm that we're using to fit. The second thing that I will say, though, is that your classification accuracy, I don't want people to think that it's decreasing, that we're making things worse. We're making things were already bad. Just because one group had good classification accuracy, the other group didn't. So rather than just focusing on the fact that one group had good accuracy, that is a result of the fact that that group was likely overrepresented in the data, in the training data itself. So it's not like this process is making things worse. It's more that things would have already been worse if the minority group was kind of more represented. We would have a different algorithm. So I want people to take kind of that piece, that it's not, we're not making things worse. Things were already pretty bad because they were so unfair from the beginning.
Just to follow up though, you are making the prediction or the accuracy of the prediction worse for the majority group, right?
Yes,
In some cases,
oftentimes, yeah, in some cases it will be worse. But that's at a trade-off of being better for the minority group. So that's why in my dissertation, I'm exploring the use of using separate algorithms. Maybe that will be the end solution, is just if you identify maybe we want better models across ethnicity or gender or race, maybe we just fit different models overall.
Yeah, that is an interesting discussion that I'm gonna I'll get to Miranda's question in a second, but Kirill asked a question that's related just to that point. You said that the model should not be based on race and gender early on, right? And I know that, there's legislation even to that effect. But the discussion we just had implies that the groups you compare, whether it's ethnicity or gender or whatever, are in fact different. Is that a situation when you would say one should likely fit different algorithms or different models, create different algorithms for the separate groups, when there is like a true difference between them?
I don't know, we have to see. So oftentimes, let's say when we're doing let's say education data and you're trying to do machine learning, you might end up having like a racial group that's very, very tiny. And so you don't have enough information of that group to do the algorithm building at all. And so in that case, you would have to train your algorithm across the entire data set. But if you do happen to have enough, whatever enough means in whatever algorithm that you're using, then that might be an option if there are two distinct differences.
Great, thank you. Okay, jumping to the other question we had here. I'm gonna read it. And that was a thought I had too, like, aren't you subject to someone asking exactly this? Isn't your test data unfair? So if you make your predictor fair by comparing to unfair, you expect errors with your prediction, right? I mean, basically you shift where the fairness happens, right? Because presumably right now you're having a proper representation of the population, and now you're shifting it to something else. Right? So that's how I understand that first question. I guess related, is the Maryland data a good data set to use for developing a model? Maryland has at least one historic Black college. Wouldn't this bias the results compared to other places with, I guess, more historic Black colleges?
So you're referring to the empirical analysis. Can you repeat the question? I'm sorry.
So, well, the first question was more conceptual. It's like, you're shifting the unfairness in the prediction to creating an unfair, quote unquote, test training set, right? And I guess the question is on the consequences. And then the second one I understand as a generalizability question, which is if you do this in Maryland and the composition is very different than other states, then you just moving the problem around. Like, that's how I understand the question.
I can answer the first one, because it's not so. When we talk about data, it's not that the data are fair or unfair, right? The data are representative of what the data, right? The data are what they are, right? And so we're training an algorithm to produce similar results across groups, right? And so what we call that, we use the word fair to imply that the algorithm is going to produce kind of what we consider equivalent results, right? We then use that algorithm on the test data. We're not requiring that the test data, we're not trying to say that the test data, we need to throw out at observations, or we're oversampling, or we're not really doing anything to the test data. We're just then applying that algorithm to the test data, right? And so the idea is that the test data, it doesn't matter whether it's like, I'm trying to think of a good, and I don't have a great heuristic for it. But the idea is that we are then feeding that data into the algorithm, and the algorithm itself is supposed to produce equal responses, right? So for example, if you are a woman and you are consistently being shown lower salaries, right? Then if you were to then make this algorithm a little bit more fair, then regardless of your gender, men and women, if everybody has kind of the similar credentials, you would be shown the same salary positions, right?
So this is interesting, this example, because it is an example where the prediction happens presumably in a setting where everyone could be better off, right? But likely we're dealing with prediction algorithms in resource constrained settings, right? Where you have to make a decision, who are the next 10 patients I can handle, or who gets support from unemployment benefits or whatever. And then I think any shift in this quote unquote fairness setup will not be a net positive for everybody. By definition, I mean, if you only have 10 slots, then you only have 10 slots, right?
Yeah, at the individual level, someone might end up with a worse outcome, but at the group level, it is a more equitable decision point. So at
Yeah.
that point, that's how you balance, like, do you care about the individual level or do you care about more at the group level?
So Stephanie has a question here. I'm gonna read that. Could you speak a bit more about the incalculable versus calculable disparate impacts? It sounds like the calculable portion of the disparate impact is estimated using the variables the applied researcher would actually have. And Stephanie said she didn't catch how much of the total disparate impact was actually calculable versus incalculable.
Yeah, so when I'm talking about incalculable disparate impact metrics, maybe I go to the slide. I'm talking about, because disparate impact is a ratio. So if you go to the formula, so many slides. The formula is the expectation of having a positive value. So if you have no positive values predicted, so no one gets a predicted value of 1, you might end up with predicted values of 0. So then you'll end up with 0 over 0. So that's why it's incalculable, but doesn't mean that there weren't any predictions made. Like the algorithm didn't fail. It's just saying that there was no predictions made for an outcome of 0, which is why we end up with having some values. So theoretically, this could mean that your algorithm is fair, just no one is being predicted in our university example. No one is being accepted into the school. Everyone is denied entry. So it could mean that the algorithm is fair. It could also mean that there's something going on, like we might not have enough of those observations in our training data. So that's why, like, when you apply lasso, but you don't do any sort of data pre-processing, there's so many that end up having 0 over 0.
Stephanie, does that answer your question? I changed your setup so that you can unmute yourself and
Yeah.
talk.
No, I appreciate it. So that's really helpful. So then I guess what I'm wondering is, in that case, it seems like when you run a bunch of different simulations and you change a lot of your simulation conditions, right? Like Frauke was talking some about changing your sampling or your rates of kind of like, upweighting your the individuals in the sensitive class or maybe in underrepresented classes. Is one way that you can measure, or is it useful to think about measuring, I don't know, when you compare the different algorithms, by what proportion of your simulations you get incalculable results, right? Because it seems like, except for the situation where nobody gets accepted, right? Like a very extreme situation, it seems like incalculable results is sort of like not useful results, because you actually don't, you're not predicting anybody to have a positive outcome and everybody's getting predicted to be a negative outcome, which seems like that's more or less just sort of like really poor model fit.
Yeah, in a sense, this was just really poor model fit. So like when I'm doing my dissertation this year, I like one of my data generating conditions is that we don't want that to happen. So in that case, I'll
Got
just
it.
recreate a new data set that we have at least one person being predicted as a positive value.
Cool. Thank you. I really appreciate your presentation. Good job.
Thank you.
Great. Thank you very much. I don't see any further hands up. Are there any final things you or Tracy would like to say? No? All right. Well, then I thank you again for presenting here for us, and I want to alert everybody to the next presentation that we have lined up for SoDa Symposium for Tuesday, December 16, with the principal data scientist from Gallup, Les Dubosclain. We will share information on exact title and abstract and whatnot through the usual channels, our newsletter, but also the social data science umd.edu website. And if you have any ideas, requests, or interest in maybe appearing in the SoDa Symposium, then please don't hesitate to reach out to me or Jody. For now, I hope all of you have a good day. And thank you so much for presenting today, Ashani and Tracy.